Hey, welcome back to chemistry. And so what we just did was we considered what the shapes of certain families of molecules would be. And so we were actually looking at pretty simple molecules to start with. We were looking at molecules where the central atom had either 2 electron groups or 3 electron groups. And so now we're going to increase the complexity a little bit, and we're going to look at molecules where the central atom has 4 electron groups. So here we go. So let's first think about what this family of molecules will look like. What will its arrangement of atoms be in 3-dimensional space? So this will be the AB4 family. And so as I think you'll see in a minute, the AB4 family, the central A atom has 4 electron groups. Okay, so let's just give you an example of a molecule that's AB4. This would be methane, or CH4. Let's draw the Lewis structure for this. So we have a carbon atom here, single bond to 1 hydrogen, another, another, another. Okay, so this is an AB4 molecule. Now, let's notice some things about carbon, the central atom here. One thing to notice is that it has no lone pairs. Another thing to notice is that let's look and count the number of bonding groups leaving the carbon. You can see that there are 4 single bonds leaving the carbon. Each single bond counts as a bonding group. So carbon has 4 bonding groups, but because it has 0 lone pairs, it basically, the central atom has 4 electron groups total. Okay, so let's draw a picture, but before we draw a picture, I need to show you what the molecule doesn't look like. Okay, so this is not what the molecule looks like. So this is what you might expect the molecule to look like. And that you basically, the angles, you might think, between the hydrogen atoms are about 90 degrees from one another, and all the atoms are in the same plane. This is not what the molecule looks like. And the reason is because what can happen is that these atoms can achieve let me say it again. These atoms can get a little further away from each other in space such that the bonds, which are full of negatively charged electrons, are shoving these atoms out in space as far away as they possibly can. So we don't want that. I'm just throwing that away. This is what a true AB4 molecule looks like. And so you can see it has sort of a 3-dimensional shape. And so what you can sort of see is that we have a hydrogen atom going up, and then we have a triangle of hydrogen atoms on the bottom. So this particular shape is called a tetrahedral shape, and the angles between the hydrogen atoms are not 90 degrees. The angles are a little bit greater than 90 degrees. They're 109.5 degrees. So the first thing I want to do is draw a picture of what this molecule looks like, trying to show its 3-dimensional shape in a 2-dimensional plane here, which is the glass board. So here's the central carbon. I'm going to draw a hydrogen like this. I'm going to draw another hydrogen like this at an angle. And so to indicate as best as I can the 3-dimensional shape of this molecule, I'm going to show a hydrogen heading out toward me with a filled-in wedge, and then a hydrogen going into the glass board with an empty wedge. And so this is how you sort of represent what a tetrahedral molecule looks like. You do need to know the angles between these bonds. So all the angles here, I'm just going to draw an angle for one of them, but all the angles are equivalent, and they're all 109.5 degrees. Okay, now let's go ahead and look at the central atom again. How many lone pairs does it have? It has 0 lone pairs. How many bonding groups does it have? And what you can see is that there are 4 single bonds, each which is a bonding group. There are 4 bonding groups. How many electron groups total are there then? It's going to be lone pairs plus bonding groups is 4 electron groups total. So what is the electron geometry of this molecule? The electron geometry of this molecule is a reflection of the total number of electron groups the central atom has. So this carbon has 4 electron groups, which happen to be 4 bonding groups or single bonds. they arrange themselves in space to get as far away as they can because they're made of negatively charged electrons. And so the electron geometry here will be tetrahedral. Now, how about the molecular geometry? So you're just looking at the arrangement of the atoms in space, and basically they mimic the arrangement of the electron groups in space. So the atoms in space are also tetrahedral. Okay, so let's go on to the next family. This next family has also a central atom with 4 electron groups. But here it's a little different than an AB4 molecule. This is an AB3 molecule with a lone pair, E. So let me give you an example of that, and then I'll talk about why it has 4 electron groups. So the classic example of that is going to be ammonia. So ammonia is NH3. So let's draw a Lewis structure for ammonia. There's nitrogen in the center, hydrogen here, hydrogen here, hydrogen here, and also don't forget about this lone pair here. So I'm hoping you can sort of see immediately that this molecule has 4 electron groups. And so there are the 3 bonding groups, the 3 single bonds, and then there is this lone pair. So there are a total of 4 electron groups around the central atom. So what is it going to look like in 3-dimensional space? So I'm going to have nitrogen as the central atom here, like this. And what I'm going to do is I'm going to put here an electron pair here. I'll put a negative sign for the electron pair, or you can leave that out. Maybe I'll just leave out the negative sign. And so we have a hydrogen here, and then going out from the plane of the glass board toward me is another hydrogen, and then going into the glass board is another hydrogen. Okay, so this is what the molecule looks like in space, but there's a little detail that you need to know, which is kind of annoying. So going back to the structure of methane, CH4, I kind of pointed out that all the angles between the hydrogens are going to be the same. They're all going to be 109.5 degrees, and I won't do the last one here. Now, you might assume that the angles between the hydrogens in this similarly shaped molecule, ammonia, will also be 109.5 degrees. But you need to know a little fact. The little fact is this: these angles between the hydrogens are not 109.5 degrees. They're actually somewhat less than 109.5 degrees. And so the angles here between the hydrogens are not, again, 109. They are 107.3 degrees. I don't think you need to really remember that number. Just know it's less than the tetrahedral angles of 109.5, but you need to know why it has less angles between these hydrogens here. In other words, why are the hydrogens in ammonia squeezed in relative to the hydrogens of methane? And the reason is that this nitrogen here is bound to a lone pair. So this lone pair here is relatively bulky. It takes up a lot of space, but on top of that, the electrons in a lone pair are somewhat more repulsive to other electrons than electrons in a shared pair. And so the electrons in a lone pair, again, because they are bulky and they are more repulsive than shared pairs, they're going to tend to shove these hydrogens together. So one fact that you sort of have to keep in mind as we're going through these structures, and this will become more clear in a minute, is that if we're looking in terms of strength of repulsiveness, so this is, if you will, repulsion strength, is going to be a lone pair interaction is going to be more repulsive than a lone paired shared pair interaction, which is more repulsive than a shared pair, let me put a greater than sign, than a shared pair interaction. So going back here in this ammonia structure, we have this lone pair that has a more repulsive interaction to the shared pairs than the shared pairs do have amongst themselves. That would be a shared pair interaction. And so that's why the hydrogens are squeezed in. Okay, so the lone pairs on the central atom are 1. The bonding groups from the central atom are 3, so there are a total of 4 electron groups. The electron geometry, you look at all the electron groups and their configuration in space, so that's the 3 shared pairs and the lone pair, and so that continues to be tetrahedral as I kind of drawn. And so, but how about the molecular geometry? Well, the best way to think of that is here is ammonia. So I have ammonia here, and you can see we have a blue nitrogen atom with 3 hydrogen atoms, and we have a lone pair. To understand what the molecular geometry is, you ignore the lone pair, you cover it up, and just look at the arrangement of atoms in space. And pretty much what you can sort of see now, when you're ignoring the lone pair, we have a pyramid here, right? We have the base of the pyramid formed by these hydrogens. We have the top of the pyramid formed by the nitrogen atom. So this is called terms of atom geometry or molecular geometry, this is called a trigonal pyramidal structure. Okay, so let me put this up here a little bit further. Trigonal pyramidal. There we go. Okay. Okay, so the last family I'm going to go over is the AB2E2 family. As you'll see, the central atom A will also have 4 electron groups around it. A good example of this is water. So let's draw the Lewis structure of water. So it looks like this. Here it is, good old water. And so what I want you to notice is that the central atom oxygen has 2 bonding groups because there are 2 single bonds here. It has 2 lone pairs, and so the total of electron groups is going to be 4. And now you can sort of see why it's called AB2E2, because the central atom oxygen, which is A, has 2 peripheral atoms B2, and then there are 2 lone pairs E2. So let's draw a 3-dimensional structure of this molecule. And so what I'm going to have here is nitrogen here, We're going to have oxygen here, and we have a lone pair here, and then what we'll have, it will have another lone pair here, and then what we're going to have from leaving the oxygen here heading out toward me is the wedge, the darkened wedge, which is hydrogen, and then going into the board is the lightened wedge, which is another hydrogen. Okay, so now here's the deal. Although the electron arrangement around the central atom is still basically tetrahedral, what are the angles between these 2 hydrogen atoms here? So you might think, because the structure is basically still tetrahedral, that it'll be 109.5. In fact, it's less than that. In fact, it's less than the angle between the hydrogens and ammonia. The angle between these hydrogens and water, which you need to know, is 104.5 degrees. And you need to know why. It's because here the central atom doesn't have just 1 lone pair like nitrogen did in ammonia. It has 2 lone pairs. So there's a lone pair here, and there's a lone pair here. And so, again, when you have 2 lone pairs, they have the strongest repulsive strength to anything else, whether it be a lone pair shared paired interaction or a shared pair other shared pair interaction. So 2 lone pairs, they're very repulsive, they're very bulky. They will squeeze the hydrogen atoms even further to give you an angle of 104.5. So to finish this off, how many lone pairs does the central atom have? It has 2. How many bonding groups does the central atom have? It has 2. How many electron groups does the central atom have? It has 4. What is the electron geometry? It continues to be tetrahedral because that is the arrangement of electron groups, whether they be lone pairs or bonding groups around the central atom. And then what is the molecular geometry? So you can sort of see it here now. Here is good old water. Now, water normally looks like that. That's how we typically see it. We have an oxygen atom in red in the center and 2 hydrogen atoms. But here I'm going to show maybe a more representative model. Here, not only are we including the hydrogen atoms bound to oxygen, but we're including the lone pairs. So this is a good model of water, but to get the molecular geometry, again, you ignore the lone pairs and just look at the atoms arrangement in space. And what you can see is that these atoms in space look bent. So the final molecular geometry of an AB2E2 molecule is bent. Let me try writing that here. Bent. There you go. Thank you for listening. We will see you next time.